Rare earth metals comprise a total of 17 elements, including scandium, yttrium, and lanthanides. Due to their unique electronic structure, rare earth elements feature optical, electrical, magnetic, and catalytic abilities not found in other elements. Consequently, they are used in particular every industry. Scandium and yttrium, for instance, are essential compounds for improving the crystal structure and mechanical properties of steels and alloys. Neodymium and cerium are the necessary raw materials for the manufacture of permanent magnets. Here are electronic parts from old computers. Recycling the rare earth metals in this part might help to meet the demand of these highly valued materials. The main needs of the recycling come from the non-renewable properties of the rare earth metals and the increase in demand. In 2021, the world mined 280,000 metric tons of rare earths. That's roughly 32 times as much as in the mid-1950s. By 2040, experts estimate we will need up to 7 times as much as we use today. In addition to mining rare earth metals directly from the mines, up to now, we have not found any other methods that can directly produce rare earth metals. So our only option is to recycle rare earth metals from existing waste containing them. All of this explains why researchers are looking to recycle these metals. Traditional rare earth metal recycling method includes extraction of rare earth metals from magnets or other electronic wastes into the aqueous phase via the use of chemical acids. Starting with mixed scrap, they couple the recovery of the rare earth metals from the ferromagnetic fraction with processing of the non-magnetic fraction to recover the base metals as well as the precious metals. In order to make rare earth metals recovery economically viable, the base metals were recovered selectively by a novel electrochemical approach that included an extraction column that enabled their separation, and the precious metals were isolated from the residue remaining after electrochemical leaching. In addition to recovering the greater fraction of the total metal content, the approach also offered improved environmental performance, due in large part of the reduced chemical and energy consumption compared to existing pyrometallurgical and hydrometallurgical alternatives. The use of strong chemical acids is not only dangerous, but also very damaging to the environment. So scientists turned their attention to more environmentally friendly and sustainable bioacids. Bioacids avoid many of the environmental hazards associated with the corrosive chemicals used in conventional hydrometallurgy, as well as the cost related to high energy, reagent, and capital requirements. Bioleaching has long been practiced for commercial recovery of some metals, in particular gold and copper, but recent researchers have been evaluating its efficacy for rare earth metal recovery, using both bacteria and fungi. By utilizing microorganisms such as Gluconbacter, which could naturally produce organic acids, can pull rare earths such as lanthanides and cerium from used catalysts or from the glowing phosphorus that makes fluorescent light glow. Although biological acid cannot reach the 99% metal extraction rate like chemical acid, and can only reach to about 25%, this conversion rate is exciting enough to give scientists confidence in future research. Neodymium ion boron magnet is the single biggest user of rare earth metals. Scientists are studying the new metal salt extraction technology that uses copper salt to leach rare earths from waste magnets from electronic products. Acid-free recovery of rare earth metals from shredded e-waste, such as hard disk drives or magnetic swaps, is possible using copper salt solutions. The fact that this selectively leaching approach can be applied to shredded hard disk drives without the energy-intensive steps of pre-separation, pre-oxidation, or demagnetization, and with no toxic waste generation, is particularly notable. This method can also effectively treat the waste liquid generated during the magnetic manufacturing process and recycle 90% to 98% rare earths from the waste materials. Although it is a chemical recycling method, the copper salt method has less than half of the carbon footprint of today's raw material development and can meet the metal purity requirements for making new magnets, which makes the application of this technology in the commercial field possible. Whether for hydrometallurgical recovery from primary or secondary sources, once the rare earth metals and other co-solubilized constituents are extracted into aqueous phase. The next tasks are separation of rare earth metals from elements other than them, follows further separation of individual rare earth metals. Another new approach for rare earth metal separation is membrane solvent extraction, which operates on the same principle as conventional solvent extraction, but the organic solvent and extracts are immobilized with the pros of a hollow fiber filter model. The aqueous phase solution and strip solution flow through the lumen and outside of the fiber, respectively. The extraction and back extraction occur simultaneously, without equilibrium limitations, and the process can operate continuously at an ambient condition and low pressure. Recoveries of larger than 95% and purities from larger than 99.5% for dysprosium, praseodymium, and neodymium were derived from magnets obtained from cell phones, hard disk drives, MRI scrap, magnet swaps, and vehicles. The low chemical usage and energy requirements, modular design that facilitates scale-up, and low operating costs are advantages compared to traditional solvent extraction. Supercapacitor is a potential energy storage system and acts as a booster to the batteries and fuel cells to provide necessary power density. In the last decades, carbon and carbonaceous material, conducting polymers, and transition metal oxide hydroxide-based electrode materials have been made to show a remarkable electrochemical performance. Rare earth materials have attracted significant research attention as an electrode material for supercapacitor applications based on their physiochemical properties. The research of electrode materials with high electrochemical activities is one of the key solutions to actualize both high energy density and high power density in a supercapacitor. Recently, scientists have developed one novel kind of rare earth metal colloidal supercapacitors, which can deliver a higher specific capacitance than electrical double-layer capacitors and traditional pseudo-capacitors. The electrode materials in colloidal supercapacitors are in situ formed electroactive colloid, which were transformed from commercial rare earth metal salts in alkaline electrolyte by chemical and electrochemical assisted co-precipitation. In these colloidal supercapacitors, multi-electron Faraday redox reaction can be utilized, which can deliver ultra-high specific capacitance, often larger than 1 electron capacitance. Multiple valence metal cations used in the designed colloidal supercapacitors. The colloidal supercapacitors can be served as the promising next-generation high-performance supercapacitors. The multiple valence metal cations in the rare earth metal cation colloidal supercapacitors can fully deliver their potential electrochemical capacitance, which can improve their cation utilization ratios. In addition, the colloid electrode can guarantee fast Faraday reaction, resulting in high power density. Scientists designed colloidal supercapacitors can represent a new promising strategy to increase the energy density of steel capacitors without the compromise of power and lifetime performance. However, some challenges need to be overcome in the present colloidal supercapacitor system. For example, the high electroactive colloidal electrode material often suffer from low cycling stability. In order to increase the long-term lifetime of colloidal steel capacitors, the following work needs to be done. The development of in situ characterization technique to observe the microscopic mechanisms of colloid evolution and cation evolution. The find of the reaction or diffusion routes of anion in metal salts during the colloidal formation process, and the find of the mechanisms of the colloid stabilizing high electroactive cations.